Hi, let's talk about Laplace transforms and in particular Laplace transforms of derivatives, because one of the big things that we can do with Laplace transforms is use them to solve differential equations, and we can talk about that in the next video. But how do we find a Laplace transform of dy dt or d2y dt squared and so on? So we'll start with the definition of Laplace transforms. We'll figure out the transforms of these derivatives, then we'll talk about how to make use of them. And I'll set you a little challenge at the end as well. So, Laplace transforms of derivatives. There's the definition of a Laplace transform. If I want to find the Laplace transform of some function, I multiply it by e to the negative st. And then I integrate from 0 to infinity with respect to t. And I end up with a function in terms of s, because I've put the limits for t in. Now, this allows me to transform something from one variable into another. T will often be time, s will often be frequency, but that's not important for this lesson. So, if I want to find the Laplace transform of y dashed, in other words dy dt, I need to multiply y dashed of t by e to the negative st and integrate it, because that's what you always do. And you can see here we've got two functions multiplied together, and we're going to have to use integration by parts. So one of the things you're going to need to be able to do is integration by parts, and I'm guessing if you're interested in Laplace transforms, you've probably done that before. So basically there's let's change the colour, there's a way of writing it where you call that u and that v dashed, and you end up with uv. So you end up integrating one of the functions and differentiating one of the functions. We're going to integrate the y dashed, and we're going to differentiate the e to the negative st. I'm not going to make this into a lesson about integration by parts, but that's the way around that I'm going to do it. So it's integrate the y dashed, and I'll get y, multiply that by e to the negative st, and I get this. So that's my uv. Minus the integral of I integrated, which is v, and the other one differentiated, which is u dashed. In this case, that's negative se to the negative st. And as I'm sure you know, two minuses make a plus. So I'm going to end up with plus the integral of s times and so on. So I end up with that. Notice I've taken the s out, because what I can see if I take the s out is that this thing, the bit without the s, is just the Laplace transform of y. That is, by definition, the Laplace transform of y. So I've got s times L of y. Now this thing here, I just need to put the limits in. One of the limits is infinity, so I'm not actually putting infinity in. I'm putting a number in and then allowing that number to tend towards infinity. So this term here, e to the minus st, is going to tend towards 0. As long as I insist s is positive. I'm going to insist s is positive. Then e tends to, I end up with e to the negative infinity, which tends towards 0. So when I put infinity in, I get 0. When I put 0 in, I get e to the 0 times y of 0. E to the 0 is 1. So I end up with that 0 minus y at 0 plus s times the Laplace transform of y, and I'll just rearrange that. So the Laplace transform of y dash is s times L of y minus y of 0, and that's important because I've gone from a function with derivatives in to a function with no derivatives in at all. So if it's something I can't integrate or can't solve, I've done this sort of fairly serious transformation into a different type of problem, and that is a formula for L of y dashed. So, you know, I would just use that as it is. Obviously wouldn't derive this every single time. One thing I wanted to mention was obviously these Laplace transforms. They're going to be a bit of a pain if you've got to do that every time. So you've got tables of Laplace transforms where someone's done it for you. So, you know, if you want the transform of sine omega t, you can just write down omega over s squared plus omega squared. It's fun and interesting to figure out, you know, to derive that using some integration by parts, and just it's a nice activity to do. It's just nice, and you know, be careful with your sides and take it slowly, and, you know, enjoy the process, and you can get from sine omega t to that, and you can try that with all these different functions. So we've derived the Laplace transform for the first derivative dy dt. Let's look at d2y dt squared, or y dash dashed. Again, I'm just going to use the definition of Laplace transform, which is integral 0 to infinity e to the minus st y double dashed of t. I'm going to do it, I'm going to do it by parts, as you'd expect. Sorry, that's supposed to be a v. The one that I'm going to integrate is this one, the y double dashed, and I'm going to get that. Integrate y double dashed, you get y dashed. This is what results from integration by parts. Minus times a minus is a plus. Take out the s, and I've got that. Now, if we look at this thing here, this is by definition the Laplace transform of y dashed. So I've got s times the Laplace transform of y dashed. And in this one, I'm going to put a number in and let it tend to infinity. I'm going to insist that s is positive, and that's going to go to 0. And then I'm going to put 0 in. I'm going to get e to the 0, which is 1, and y dashed of 0. Now, sorry, that's what I've got there. Now, I know that L of y dashed, I've just derived it 2 minutes ago. L of y dashed is s L of y minus y of 0. So I'm going to replace my L of y dashed with what I derived. I'm going to multiply it by s, and I'm going to subtract y dashed of 0. L of y dashed, multiply it by s, subtract y dashed of 0, because that came from the second limit. So that's going to be s squared L of y minus sy of 0 minus y dashed of 0. And that is the Laplace transform of the second derivative. So, a challenge for you, if you feel like it, find the formula for the Laplace transform of y triple dashed. Do the same way. Then, if you're feeling really on the ball, see if you can find the Laplace transform of the nth derivative of y. So you might be able to spot a pattern. You might be able to continue that pattern and think, what would it be for the nth derivative? See if you can do that. So that's it. Laplace transforms of derivatives, and we can use those for solving a differential equation, say like this one. So equals some function of t. So if I've got some second order differential equation, I can take Laplace transforms of it. We'll do a video on that later. Okay? Thanks for watching.